So if I had a horizontal plate and I put it 10 feet under the water, there's going to be a force acting on this plate. Agreed? And it was our job to figure out the force on the plate. Does this sound familiar? It is, right? So what we did is we said the reason that there's a force on this plate is because there is an entire column of water sitting on top of this plate. That column of water is 10 feet by 3 feet by 2 feet. The force on the plate is equal to the weight of the water. Let's do units here. So water, just a fact, has a weight of 62.5 pounds per cubic feet. And then, if I'm calculating the volume of this block, it's 10 feet by 3 feet by 2 feet. And whatever this number comes up to is going to tell us, well, the units are going to be pounds. It's going to be how many pounds of force is on this block. And what I want you to see here is the calculation. At 62.5 is the density. The 10 feet is the depth. And this 3 foot times 2 foot gives us the area. So when we're talking about the force on something, is what you want to remember, the calculation of force is going to be density times depth times area. Let's talk about this. There's two words that should bring up a similar idea when you talk about this. Mathematically, they're slightly different. Pressure is pounds per square feet, and force is measured in pounds. So I'm not going to work through it, but you see that. Oh, how do we get pressure? These two give us pressure. So density times depth gives us the pounds per square feet, and then times the area times square feet gives us the pounds. So another idea for how these work is no matter how I've got this plate oriented, is the part, no matter what the depth, if the depth is the same, no matter what the orientation is on the plate, the pressure is going to be the same. And the way your book explains that if I'm underwater, the pressure I feel on my nose is going to be the same thing as the same pressure as the pressure on my ear. So it's these ideas that are going to allow us to use an integral to calculate forces.
Wait, why was the depth 10 feet?
Say that again?
Why was the depth 10 feet?
I was given.
Oh, that's a 10? I thought it was a 6.
That is a 10. So, somewhere, a worked out example. So here's the water, and 2 feet below the water, I've got a rectangle, and not really to scale. It's 5 foot by 3 foot. And I want to find the force on this plate. And just so we're clear, the orientation is the water's up here, so this is underwater, and the plate is vertical like this. The horizontal ones, when we did originally, it's more interesting if it's vertical. And what's interesting about this is you see that different parts of the plate are at different depths. So the pressure here is more than the pressure up there. What we're going to do is remember that pressure times area is force, is we're going to group together all the points that have the same pressure on them. The pressure depends on the depth. So our slices, we're going to take all of those together. We want to come up, we want to have a coordinate system. We want to be able to measure everything. So I need to measure the depth. I'm going to put y equals 0 at the very bottom of this. Oh, how far have we gone in this? And this is the last one we did?
Yeah.
Okay. So this will be just a gentle reminder. And then where is your water level? Y equals 5. So again, y represents how far we are from the bottom of the rectangle. And from the bottom of the rectangle to the top of the water is 5. So I want to find the force on this slice. Do you remember the formula for finding force? It's multiplying 3 things together. Density times depth times area. Okay, so the depth, if I went up by 1, that would be 4 feet under the water. If I went up by 2, that would be 3 feet under the water. In general, if I went up by a generic amount y, how far under the water am I? 5 minus y or y minus 5?
5 minus 1.
It's always the big one minus the small one. And then for the area calculations, it's a rectangle, so it's base times the height. The base of this rectangle is 3 feet. And how tall is this rectangle? dx or dy? dy. It's a small vertical distance, so that's a dy. So density?
That's 5.
That's 5. Good point. That's what I said. 5, right? Yeah. So 62.5 for density. The depth is 5 minus y. And the area, base times height of this rectangle, is 5 dy. And then the whole point of these last 2 chapters that you're going to be tested on next week is, once you've made the calculation for one small slice, how do you add all of those up? An integral. And it's this axis we introduced, is we're using that to index the slices. So there's one slice at y equals 1. What's the range of slices, or the range of y values that give us the slices that make up this entire rectangle? The y at the bottom? And the y at the top? So this integral represents some number. Feet, pounds per cubic feet times feet times feet times feet. Each slice weighs how many pounds, and then adding up a bunch of pounds gives me more pounds. So the units on this are pounds. It's the number of pounds that are the force of the water on this plate. That's really all there is to it. There's a couple things that might come up.
So the density always going to be 2.5.
Yeah, all the problems I'm going to do in class are water. And if you get another liquid, they'll give you the density. Yeah, and I'll tell on the exam, I'll remind you that it's 62.5.
Do we need to solve that on the exam?
No. No, absolutely not. So if you heard that question, it's can you stop here or do you need to give me a number? And the answer is, I just want to see that you can read the problem and translate it into a calculus. So whatever they're asking gets translated into a calculus problem. So on the exam, you stop here. So I've already tested you on your integration skills. That was last test. This test is I'm going to test you on how good you are at reading a problem and setting up an integral that will answer that problem. What do you think is the more useful skill?
The latter.
Actually setting them up. This technology can evaluate them easily. So all of these problems are, we're going to have a picture of something that's underwater, and it's your job to figure out the force on this shape. They're always vertical strips, because we want to collect together all the points that make up, or all the points that have the same pressure. And do you see that when I'm doing the area calculations, I'm going to have to keep track of a horizontal distance, and when I'm doing the depth calculations, I'm going to keep track of a y distance? And so that means that instead of just a y-axis, I'm going to need an x-axis and a y-axis for this problem. So the first thing you want to do is introduce your coordinate system. Previous problem, you only needed 1 dimensions. This we need 2. And there's different people have different ways of doing this. One of my colleagues follows the book, always puts the water level at y equals 0 and positive y is down. What I prefer to do is just you pick how you want your coordinate system to work. And I like positive y up. So I'm thinking I'm going to put the origin here. It's like as good a place as any. And I'll put positive y up. So first step is always to get the coordinate system. Second step is to get the equation of the water line. So the water line is at the horizontal line y equals 10. It's still a 10, right?
The way it keeps looking like a 6.
How's that? 10.
Okay, that works.
Can you ever read that?
Okay, you don't have to do that.
No.
Okay, so first of all, find the force on the entire plate. We're going to figure out the force on each slice, add all those up. And how do you calculate a force? So you multiply, there's 3 factors. So density times depth times area. Actually, let's draw a picture here. That's y equals 10. Here is my slice. So what's the depth here? So that's why I have you find the water level second, because the depth is always water level minus y. And then this is a generic xy point here. It's actually for y. There's x, there's y. dy. How far across? Yeah, do you see that that's a horizontal distance, which would be x? So that area is x times dy. And so that means that the total force on the plate is going to be, adding all these up, 62.5 and minus yx dy. And what are the y values? The y value for the very bottom slice in this plate, and the y value for the very top. So this would be 0. Yeah.
Why is it x about 10 on the bottom?
Oh, it's because different x values are going to have different. Okay. Why are you going to get points taken off if you write that as your answer? Yeah, that x clashes with the dy. So now what we need to do is get an algebraic relationship between all the x, y points on this line. And then we can substitute into that. So let's do it. What's the slope of this line? Down 10 over 10? Minus 1. What's the y-intercept? 10. So is that okay for the equation of that line? Slope's -1, y-intercept's 10. And turning this around, we get x equals 10 minus 1. I'll replace this x by 10 minus 1. So if I found a way to get these lectures onto YouTube, would you still come to class? Yeah? Okay.
That's a hard one.
I know. So I like the idea of having the lectures available for you to watch and pause. But what I worry about is you might not come to class.
We can't ask screen questions.
That's true. You cannot ask the screen questions.
Unless you just hover in the comments all the time, it'd be great.
Yeah, that would. That wouldn't happen, but yes, that would be great. So anyway, I'm going to try to get these onto YouTube. Do a pilot program. Everybody cool with that? What's it? Oh, if it happens, it'll be a private channel, and I'll put as an announcement on the campus. Fingers crossed. Yeah, in theory, I like the idea, because that way you can, if you want to see me rewind and do something again, or if you want to pause me so you can take notes. Here's the water. And 15 feet under the water is the floor. It's about somewhere out in the bay. And then I have a circle of radius 2 feet that's standing up horizontally here. So I've got a little submarine up there. But I have something, and I want to calculate the force on this plate. So, coincidentally, we've just been doing problems like this. What's the first thing you want to do? Put in the coordinate system. And my idea is to put in the coordinate system the easiest possible coordinate system to work with. And for me, it would be the one where the origin went right through the center of the circle. Different people have different feelings about this. For me, that's the obvious coordinate system. And given that I'm going to put my origin right there, the next thing I want you to do, I'm going to erase over there while you're catching up, is give me the equation of the water line. It's going to be y equals something. Is what y value do all the points on the surface of the water have? Y equals? So it's 15 to the bottom. This isn't even at the bottom yet. There's no way it can be 17. It can't be more than 17. Agree? Yeah, so it's 2 to get up to the y equals 0 part. And it was 15 total. So this distance is 2, the whole thing is 15. That means it's got to be 13 left.
Not around mine.
Yeah, ballpark.
Not mine.
Close enough. I'm going to take a slice like this. So I like to redraw this so I'm not looking at the whole shape. And if it helps, that is a generic XY slice. So to calculate the force on a slice, density times depth times area. Density is, for all of these problems, I'm going to use 62.5. The homework might be under some kerosene. So maybe it's kerosene or a different type of liquid, or maybe we're not on Earth. 62.5 for us. Oh, actually, yeah, that's one thing we need to talk about. I'll give you that number on the test. What about the depth? Minus y. And that area, so I want you to write down the expression for the area. It's a mistake that some students make here. So if you're the type of student who would make this mistake, I'd rather you make it now and we correct it. So I think everybody's comfortable with the dy. What's the base of this rectangle? It is not x. Yeah, remember that what does x represent? X is the horizontal distance from the y-axis. So that distance is x. And you see that this whole thing is going to be 2x. So the area is 2x times dy. Let's get the limits there. What's the y value for the very bottom slice of this circle? -2, right? So what down here we're at the negative y's. So y equals -2. And for each y value, until I get to y equals 2, I'm going to be adding up slices. So far, so good? And the one thing I have to fix is that x, which clashes with the dy. So I'm on a circle. The center is 0, 0. And the radius is 2. There's an equation for that. X squared plus y squared is. Do I want to get an x equals, or do I want to get a y equals? X equals, right? We're trying to get rid of the x and replace it by something with y's. So if x squared is 4 minus y squared, that means x is square root 4 minus y squared. And that is full credit. Did we talk about imperial? Actually, yeah, we should talk about this again. Yeah, so there's what we call SI, meters, kilograms, and all that. And have we talked about this? Okay. So it's there's two ways I can measure distance. I can either say something is 5 feet, or, I know they're not the same, but I could say something else is 3 meters. You can either measure distance in feet or meters, right? Who uses feet? Right, the U.S. And there's a couple other countries. Myanmar does, and Liberia does, and there's 3. And who uses meters? Everybody else? So pretty much, these are the U.S. units, and this is everybody else. So what's the only country who has put somebody on the moon? U.S. So which are the superior units? U.S.
Yeah, Russia put someone, didn't the Soviet Union put someone on the moon too?
They did not. They put somebody into space. They did not get anybody on the moon.
Really?
Really? Yeah, Soviets never got anybody on the moon. So they were the first one. They got, Yuri Gagarin was the first one who made it into space. They never made it to the moon.
Not China went into space,
Yeah, they did.
but they did land on the moon.
They did not. Only the U.S. who used the superior feet system.
And then when a Canadian airliner accidentally filled with liters instead of gallons, and they ran out of fuel.
Really?
Yeah.
See? That was their own damn fault.
But that was an isolated incident.
Okay. So the U.S. measures things in feet, and the rest of the world measures distance in meters. Okay, and then we've got other units. Is the U.S. measures force in pounds, and how does the rest of the world measure force? Yeah, it's measured in newtons. And so some of your homework problems are you're going to work with the density of water is 1,000 kilograms per cubic meter. If you do this density times volume, do you get force? You do not. So the problem is kilograms are a measure of mass, not force. So you're going to need a conversion factor. And on Earth, the conversion is 9.8 newtons per kilogram. So when you're doing density of water and they're measuring things in newtons, it's used 9,800 newtons per cubic meter.
So wait, are pounds used to measure mass?
No, pounds are a force. So it's the missing unit here, which people don't talk about very often, is a slug. So a slug is the U.S. way of measuring mass.
How much is a slug?
The conversion factor is 32. The conversion factor is 32. So it's 32 slugs per pound.
Why is it called a slug?
I have no idea.
What is it like?
I imagine like
Slugs or like slug to the arm?
no, it's I would never do this, but some of my friends of mine It's when they'd go to the arcade, they'd have these kind of pieces of metal which almost look like a quarter. Those are called slugs. So I imagine that's something to do
I was
with
thinking
that.
of I forget I know there's an object called slug.
Yeah, they get in my garden and I pour beer on them to get rid of them. Oh, so did you know it's actually, if you want to get rid of the slugs in your garden, just take a little dish of beer. Because they love beer, so they'll go to it and then they'll go in the ground.
Oh, man.
One time I found a slug while washing vegetables.
Oh, doing what?
Washing vegetables.
Oh, okay, that's good. That's how you know it's organic, right?
It was still alive.
Okay. So far, so good. So again, you're doing homework. Well, in class, we'll always use the superior system and say that water is always 62.5 pounds per cubic feet. But if you're doing a homework problem, they might have some kilograms or meters or something. This is your conversion factor. So this is the last example I'm going to expect you to do. So I'm going to have you try to do it by yourself. So now, this is a dam. This is a big wall with a bunch of water behind it. So the dam is 100 feet tall, and the water level is 15 feet below that. And we've got a gate here with a semicircle that if the water level gets too high, we're going to raise up that gate and let the water through. And the semicircle has a radius of 20 feet. So because it gets underwater here, there's going to be a force on it.
A diameter?
Diameter is 20. So, what did I say, radius?
Yeah.
Okay. I meant to say diameter. The diameter is 20 feet. So, in this situation, I want to know the force that's on the plate. We set up an integral for me that will calculate that.